Welcome to Algebra 2. This is section 2.1, Transformations of Quadratic Functions. All right, to introduce this section, what we're going to do is tie it into chapter 1. One really nice thing about our textbook, our new textbook that we've gotten, is that they do a nice job of building on concepts that we've covered earlier in the year and keep practicing those skills. So this first one here, we want to describe the transformation, and this chapter we're looking a lot at quadratic functions, at parabolas. So we want to describe the transformation from the parent parabola, the parent quadratic function, f of x equals x squared. Now, I'm sure that most of you, I would hope, can look at these and tell me exactly what's going on in each one. So what I want you to do right now is just pause the video for a second and jot down what you feel the transformations are, and I'm going to go through them here in a few seconds. All right, hopefully we've got some ideas down on paper here. So problem number 1 here, g of x is negative quantity x minus 2, that quantity squared. Well, as far as the inputs are concerned, we're subtracting 2 from our inputs. That indicates a shift of 2 units to the right. And there's a negative sign out in front. That's affecting the entire function, not just the input, not just the x. So that affects the graph vertically, and it negates the height. So that's a vertical flip. And again, we should all be very comfortable with this at this stage of the game after chapter 1. For problem number 2, here we've got a negative 2 inside yet again. So again, that's 2 units right. And then we've got a plus 2. That's affecting the entire function, not just the input. So that is 2 units up, adding 2 to the height. For number 3, here we've got that negative sign outside the function again. That is a vertical flip. Then we've got plus 2 inside, affecting our input. That is 2 units to the left. Remember, that's bizarro world. You'd think it should be moving to the right when we add 2, but it's not. It's moving to the left. We're 2 days ahead of schedule. All right, and then the minus 2, that's affecting the whole function. That is 2 units down. And they really like their 2's here in this example. And then this really should be number 4. Oops. Be careful when you copy and paste, viewers. All right, here we've got a 1/2. That's outside the function. It's affecting our output. It is 1/2 as tall. You could say vertical compression by a factor of 1/2. Then we've got our 2 units to the right and 2 units down. Again, noting the difference. What happens when we adjust inside versus outside? Problem number 5. Here we've got twice as tall. Again, when it's affecting the whole function, it's affecting the height. And then yet again, we are 2 units to the right. And lastly, number 6. Let's rattle through these. We've got a vertical flip. We are 2 units to the left. And we are 2 units up. All right. Now, I just want to add one in there just for kind of a little bonus here. What would happen if we had like g of x equals, and let's say it was 1/2 x squared. This is one that I find is very commonly missed. What happens when we're doing an adjustment to our input that's a multiplier? So here, again, inside we're thinking speed, left and right, our time axis, our x-axis. So you'd think this would be going or covering half the area left and right, but that's really not the case. Remember, that's one of our bizarro world principles here. So this 1/2 x is really saying half as fast. Another way of saying that is if it's moving half as fast, that means it is 2 times as wide, moving much more slowly across the coordinate plane. All right, our important terms for today: a quadratic function, the function where the highest power that an input is raised to is 2. So we see something squared. Okay, and first off here in 2.1, we're looking at the vertex form. We're going to have a few different forms this chapter. And that you can see we have a lot of our numbers that would affect the transformation of the graph. We have an A out in front, and that tells us how tall or is there a vertical flip if it's negative. We've got our h, which is a left or right shift. And then we've got our k, which is an up or down shift. And again, we've seen those through examples when we went through pretty much all of chapter 1. We arrived at those conclusions. The graph that you get by plotting a quadratic function is a parabola. Again, we saw that at the start of the school year. The vertex of a parabola is the point h comma k, so that ties in with our vertex form. And that is the point where the graph is bending the most. And as we're going to come to see it further on in the chapter, that's going to be the maximum or the minimum point of that parabola. All right, so first example, describe the transformation, very much like our intro, except now we're going to look at a little bit more complicated quadratics here. So for number 10, g of x is quantity x minus 9 squared plus 5. Didn't mean to do that. Inside the quantity, affecting our input is minus 9. So that's telling us that we are moving 9 units to the right. And then the plus 5 outside, that's adding 5 onto the height. It's adding onto the entire function, so 5 units up. All right, and then problem number 12, similar adjustments here. Now we're going 10 units to the left and 3 units down. Again, adding and subtracting inside the function with our input and outside. Just getting a feel for those adjustments. All right, next we start looking at some multipliers. For number 22, g of x equals negative 2 times x, and then that squared. All right, well, with our input, that's going 2 times as fast, twice as fast. So we could also think of that as being half as wide, or a horizontal compression. Then we've got a negative sign out front indicating a vertical flip. Right, we're negating the entire function, negating the height, flipping it upside down, vertical flip. Could also call that flipping over the x-axis. I believe our textbook uses that. I like the word vertical, personally. All right, 24. Here we've got, with our input, we've got 1 unit to the right. And then we've got half as tall. Okay, you can see 1/2 times the entire function. That's 1/2 times the height. So half as tall. Good descriptor there. And again, this section should be a very smooth transition into chapter 2. Really like how they connect that information together. It's a nice job. Pat on the back to the textbook authors here. All right, here, looking at our vertex form, describe the transformation from its parent function, then identify the vertex. All right, so here you can see we've added more and more adjustments to our function. We've got a lot going on here. We've got a vertical flip. We are negating the height. It is 4 times as tall. And we have shifted that graph 1 unit to the left. And we've also shifted that unit 5 units, or shifted that graph 5 units down. Where would the vertex be? Well, that's the ordered pair, x minus h. I must have done minus -1 here, and then k units down, so minus 5. Okay, and that again shows us from the origin we moved 1 to the left. That would be -1, and then down 5 units. The shift here really does play into our vertex quite nicely. All right, for number 30, we've got half as tall, or a vertical compression, something like that, and then a shift of 1 unit right. Okay, that would make our vertex the point we went 1 unit to the right, +1, we moved away from the origin, and then we didn't move any amount up or down, right? There's no k value here. We could assume that to be a +0. There was no change in height, no change in y. Cruising right through this lesson. Example 4. Here's where things get a little bit more interesting. Write a rule for function g described by the transformations of function f. Then identify the vertex of g. Okay, so we need to come up with this function g, and they're telling us, first of all, we've got a function f that is not just x squared. So we're working with It was like, instead of a parent function, we've got a grandparent function. And here's the parent, we need to come up with the child. So we're going to take this function f, shrink it by a factor of 1/2, and then translate it 1 unit down, and then reflect it across the x-axis. So we got a lot going on. So let's start with our f of x. Okay, the first thing that happens is it is shrunk horizontally. Okay, that means if it's a horizontal shrink, it means it must be going twice as fast. If it's only, covering half the ground left to right that it used to. And a translation of 1 unit down. So now this next unit, I don't want to end with g, that's got to be the name of my final one, but I'm going to kind of use a placeholder here, h of x. And I'm going to say, okay, well, what I'm doing is, if I'm doing a horizontal shrink, then that's f of twice as fast, 2x, affecting the input, and then I'm translating it 1 unit down. So I'm taking the function, plugging in 2x to go twice as fast, and then subtracting 1. Okay, well, that tells me that h of x, this kind of stepping stone function, f of 2x would be 2x plus 6 squared plus 3. And then remember, we subtracted 1 from it at the end. And h of x is then equal to, we'll leave it as 2x plus 6 squared plus 2. Okay, then we need to account for the reflection in the x-axis. So we're reflecting across the x-axis. If here's our coordinate plane, we're reflecting across that axis. That's a vertical flip. So now my function g is just going to equal the negated function h. Right? H took care of the first part, and then the followed by, that's where we bring it all together with function g. So g of x is then going to equal my h of x, but negated. 2x plus 6 squared plus 2. And I should be negating all of that. So it actually equals negative 2x plus 6 squared minus 2. That negative sign distributes to that 2 as well. All right, so here's our function g of x. Now we need to use that to find the vertex. Well, you'll see here that we don't have just x minus h in there. There's a 2 in the way. So I wonder if we can't manipulate g of x to look a little bit nicer. So what if I take a greatest common factor of 2 out? Right there, I can see we've got a little x minus h action happening in there. And if I'm squaring the product of 2 terms, that's going to be the same thing. Just like if we had 2x squared, if we're squaring all of that, 2 times x, it would be 4 times x squared. We would square both. We do the same thing here. Negative, and then 4 times x plus 3 squared minus 2. All right, and now we can pretty clearly see what our h and k values are. The vertex of g is going to be the point -3, -2. All right, and of course we could type this function g of x into our calculator and make sure that that's showing us exactly what we want to see with f of x, but I can assure you that's going to be the right answer. And example 5, our final example here, we've cruised through this. The function f of t equals -16t squared plus 10 models the height of an object dropped from 10 feet after t seconds. The same object dropped on the moon is modeled by g of t equals -8/3 t squared plus 10. Describe the transformation from f to g. From what height must the object be dropped on the moon so that it hits the ground at the same time as on Earth? Now this is a very cool problem, very interesting problem. So you can see the only change is this 16 turned into an 8/3. So something affected our how fast, right? Is this graph moving? And if you think about it, if we have time and the height of an object on Earth, then naturally if we start off at a certain height, it's going to fall quickly. And if we do that on the moon, same axes of time and height, we start at the same height, it's going to take much longer for that object to reach a height of 0. So it's going to cover much more distance this way. So it's going a certain factor slower. All right, well, what is the transformation from F to G? Well, we want to know, we did 16 times some other number, I'll just call it A, to get to 8/3. And this is just going to be how we figure out the how much, how many times is fast. And if we divide both sides by 16, or multiply by 1/16, makes the fraction work a little bit easier. I've got an 8 multiplied into the top, a 16, which is 2 8s multiplied into the bottom. So I can simplify that 8 over 16 as 1 over 2. And what I find is that this A variable is 1/6. All right, so describe the transformation. We could say that g of x is 1/6 as fast as f of x, or I guess I should be using t's. G of t is 1/6 as fast as f of t, or we could say g of t is horizontally stretched by a factor of 6. Right, because this graph over here showed that the graph was moving slower, but it also showed that we stretched that graph out, so it's 6 times as wide. All right, from what height must the object be dropped on the moon so that it hits the ground at the same time as on Earth? Now, I love this. I'm actually going to change the color of my pen for the second part of the problem. Nice blue. This is actually very interesting. When we're talking about height, we're talking about the output, the f of, the g of, right? The output is the height, the input is the time, the t value. So we want to know from what height must the object be dropped on the moon? So we're trying to find the g of t. Must that be dropped so it hits the ground at the same time as on Earth? Oh, I'm sorry, I'm going about this kind of backwards, aren't I? What we want to know is, here, let me erase a bit there. We'll go back to our lovely little blue pen. Okay, we need to find out when or at what time the object hits Earth. It hits the Earth when f of t equals 0. Again, I'm trying to answer when here to ultimately lead to a starting height. And as we can tell from our functions, we're starting off with heights of 10. Well, we want to change that 10 in our g of t so that we have the same result as when we have this certain time increment. Okay, so if I want to find out when f of t equals 0, when does 0 equal negative 16t squared plus 10? That is, when does 16t squared equal 10? When does t squared equal 10 over 16? If I square root both sides, I find that t equals plus or minus root 10, square root of the top, over 4, square root of the bottom. And really, we only want the positive result there because time travel hasn't been invented yet. We can't go back in time. So at that time, the object hits the Earth. So we want to know g of t Well, that height is going to be 0 when it hits the moon. That equals negative 8/3 times root 10 over 4, the time it took to hit Earth, squared, plus what value? And we'll just call this one h, the height, the starting height. So let's see, 0 equals negative 8/3, square the top, square the bottom, plus h, just following order of operations now. And again, we've got that 8 over 16, which can be 1 over 2. And then we've got 10 over 2, which can become 5 over 1. So h is going to equal, across the top, negative 1 times 5, and across the bottom, 3 times 1. So that height is negative 5/3 feet. That is a very challenging second half to this problem, but also a very, useful progression to go through and say, okay, what are we trying to find? What do we need to know? What can we find right away with the given information? How do we break down these functions? So very, very, very good problem. I really like this one a lot. All right, there's a look at your assignment. Notice no graphing. We are going to have plenty of opportunities to graph these problems later on. We want you to get the practice with the transformations, not exhaust you with graphing them. All right, so that does it for section 2.1. I hope you've enjoyed it.